Batch reactor
Isothermal
overview.
batch reactor.
This video will contain some basic information.
In this video,
on the most
we will
commonly
cover an
used
example of an
reactors for a
isothermal
variety of
batch
different
reactor.
projects. And
The
we'll
example
explain
tells
when you
us
would and
that we
would
are
not
doing a
use batch
copolymerization of styrene and butadiene
Assumptions that are
in an
commonly made for a
isothermal batch reactor,
is that it contains
and asks us what the final
it is
concentration
contained
would
in
be
a closed
after
system.
10 hours of operation.
Most often, batch reactors are used for liquids.
Assumptions that can be made
And we also
for this
assume
problem is that the reactor is both
well
isothermal
mixed,
and
therefore
isobaric,
concentration and temperature
and that we can
do not
assume
vary
constant
throughout the
density.
tank. Cooling in
The
a batch
reaction is given
is done
as
using
S
external
plus
heating
3.2 B goes
This
to the
controls
polymer.
the temperature of the reactants
And the
case
rate of
isothermic
reaction is negative RS is equal to Ka times the
Scale-ups for
concentration of
batch reactor is
styrene
usually
times the
quite
concentration
simple.
of butadiene, where
both
Ka is equal to
isothermal and
0.036
systems,
meters
in which
cubed
no
per
heat is
kilomole
added or
hour.
removed. The system scales up with
So
volume.
additional information on
because
the problem
concentration
is that
over time does not
We
change.
start with 2,200
The main
kilograms
difference
of styrene
in scale up
and
of a batch
5,000
reactor
kilograms
is in
of
terms of
butadiene.
heat transfer.
The reactor volume
As you
is
increase
27
volume,
meters
your
cubed,
surface area does not
and we are
increase
provided
as
with the
quickly.
molecular weights
And therefore,
of both
there is less
styrene
room for
and
heat
butadiene.
transfer.
Please
If we
take a
start with
second
a
to pause
reactor
this
with a
video and see
diameter
if you
of
can do the
1,
problem
whose
yourself.
volume and surface area are also 1. When we increase the diameter by a factor of 10, our volume increases by a
The
magnitude
first step
of
to this
3,
problem
and the
is to
surface
start with an
area only
overall
increases
mass
by a
balance.
magnitude of 2.
This is the change in moles
The
over
mole balance
time,
of a batch
which is
reactor
equal
can be
to
used to
the
demonstrate
entering
why
flow rate
concentration
minus the
is the
exiting
only
flow
thing
rate
necessary for scale
plus
up.
the rate of generation.
Using a standard
Since there is
A
no
to B
flow
system,
in or out of a batch reactor,
we know that the
those
total
terms can be
moles
eliminated.
of species A per time
We
is
are
equal
left
to
with
the rate of
DNS
reaction
over
times the
dt
volume.
is equal to RS
Given a
times
rate
the
law,
volume.
such as this second order one,
An equivalent
we
mole
can then
balance
substitute
can also
into
be
the
written for
original
butadiene.
equation and get that dNA over dt is equal to negative Ka.
Our second
Ca
step is the
squared
rate of reaction.
times the volume. Noting
The
that
rate
Na
law
is
was
equal
given to
Ca
us
times
as
the volume.
negative RS
We
is
can
equal
see that
to the reaction
the volume terms
rate
cancel out.
constant times the concentration of styrene.
This leaves
times
us
the
with
concentration of butadiene.
Ca over dt is equal to negative
We need a
Ka
rate law for both
Ca
styrene
squared.
and butadiene for
This
the mole
clearly
balances,
demonstrates
and therefore
that
we
volume
use
does not
relative
play a
rates of
role
reaction.
in the scale-up process of a batch reactor.
Using the stoichiometric coefficients,
So why would we
can
ever
write
want to
that
use
the
a
relative
batch
rates
reactor?
as
In the
RS
case where
over negative 1
you want a
is
small
equal
scale
to
production,
RB
such
over
as
negative
drugs
3
or
dyes.
dyes.
Therefore,
When you are implementing
RB
a
is
new
equal to
process or an
3.2
untried
RS.
reaction. When the material
The
is
last
of
thing
high
we need to
value,
do is stoichiometry.
when there is a long reaction time,
Since our rate laws are in
and there's rapid
concentration
fouling
and
of
we
the
are given
reactants or
moles,
products,
we need to set up a relationship.
contamination and fermentation occurs easily.
Concentration is equal to the total moles divided by volume
When would you
and
not
the
want
molecular
to use
weight
batch
of the
reactor?
species.
When there is poor mixing in the
At
system,
this point, all there is required
There's
is that we
impurities.
use a differential equation solver
there's
such
heat
as
transfer in
Polymath
the
to find the
system.
final concentrations.
longer startup times,
The following equations
or when the
are
reactor
what would be
materials
necessary to
contain
get a
catalytic
solution using
properties.
Polymath. As you can see, the code contains our differential mole balances with initial conditions, our rate laws, the concentrations of butadiene and styrene, as well as the given constants. We must also put the initial and final times of the reactor. The initial time of the reactor is 0, and the final time is 10 hours. The developed concentration profile looks like this. It's difficult to see what is happening, but we have both the concentrations of styrene and butadiene decreasing because they are reacting irreversibly. The butadiene is reacting slightly faster than that of styrene, since our reaction was S plus 3.2B goes to polymer. The final concentrations of butadiene and styrene should be given as 3.37 kilomoles per meter cubed of butadiene and 0.77 kilomoles per meter cubed of styrene.